everyone, thank you so much for joining this video. Our learning objective today will be to be able to use graphical methods to find the activation energy for a reaction from experimental data. And then we're going to look at a core practical, which is finding the activation energy of a reaction. Now we're going to talk about the Arrhenius equation. And what this equation calculates is the rate constant, K. So we get an exact value for the rate constant. So there are two things to note. The first is that the bigger the rate constant, the faster the reaction. And that's because for reactions, we normally have rate equals K times something. So that means that if this K is a lot bigger, then the rate will be a lot faster. And the second thing is that the higher the temperature, the faster the rate of reaction. And that's because when we increase the temperature, the particles move with more kinetic energy. So there are more collisions per unit time. More of the particles have that activation energy required to successfully collide. So that means that there are more successful collisions per unit time, so the rate of reaction is faster. And now I'm going to quickly go through this equation and what all the letters stand for. So first we have the rate constant, which is K. And this, the units of this depend on the order of reaction. And then this EA is the activation energy. And then T is the temperature. And that's measured in Kelvin. The activation energy is measured in joules. And then this R here is the gas constant. And that's measured in joules per mole per Kelvin. And that's usually given as 8.31 because it's a constant. And then A stands for the Arrhenius constant. And this has the same units as K. So it depends on the orders of reaction again. And then this E is a mathematical number, and this is the exponential. And this can be used on the calculator by typing in shift and then ln. Now we're going to look at some graphical analysis. So we have this equation here. If you don't know how I got this equation, then go back to the video where I worked out the activation energy required from Arrhenius's equation. And so we can plot a straight line graph from this equation that we have here. And that's because we know that straight line graphs have the general form y equals mx plus c. And so we can make this into the form y equals mx plus c. So we have y, and we can make ln a equal to c, and then we have mx. And so this gives us that the y would be equivalent to ln k, m would be equivalent to minus EA over R, the x would be equivalent to 1 over t, and c would be equivalent to ln a. And so the graph we get would be like this. So on the y-axis, we would have ln k, and on the x-axis, we would have 1 over t plotted. And then the graph should look something like this, because the gradient, which is the m, this is the gradient, is negative. And so this gradient would be equal to minus EA over R. So the way you find activation energy would be to find the gradient of the graph. So that would be to draw a little triangle here and divide the difference in the y by the difference in the x, you do the gradient multiplied by minus the gas constant. And then this point here, this would be our ln A, because C is the y-intercept. And so that's how you can find the Arrhenius constant. So you would unlog it to find A, and you can find the activation energy by doing gradient times by minus the gas constant. Now we're going to look at a required practical. So we're going to look at finding the activation energy of a reaction. So what we do is, firstly, we prepare 10 centimeters cubed of phenol solution and 10 centimeters cubed of bromide-bromate solution into one boiling tube. We then add 4 drops of methyl red indicator to the mixture and pipette in 5 centimeters cubed of sulfuric acid. We put that into another boiling tube, and then we use a kettle and a beaker to prepare a water bath with a temperature of 75 degrees Celsius and stand the 2 boiling tubes in the water bath. When the contents of the boiling tubes have reached the water temperature, mix the contents of the 2 tubes by pouring rapidly from one tube into the other and then pouring the mixture back into the empty test tube. Start the stop clock at the same time. We then leave the boiling tube containing the reaction mixture in the water and time until the methyl red indicator disappears. We then copy the results table below and use the first 2 columns to record all the results. And we repeat the experiment at 65, 55, 45, 35, 25 and 15 degrees and use ice to achieve the lowest temperature. So then we can be able to plot a graph. So first we have the relationship of ln K equals ln A minus EA over RT. And so if we plot a graph of ln K over 1 over T, and it might look something like this, then the gradient found by the difference in the y divided by the difference in x that will be equal to minus activation energy over R. And so to find the activation energy, we would need to do the gradient multiplied by the negative of the gas constant, which is 8.31. Now we're going to move on to some questions. So for the first question, calculate the rate constant with and without a catalyst in a reaction where the Arrhenius constant A equals 6.92 times 10 to the 6 seconds to minus 1, and the activation energy equals 150 kilojoules per mole without a catalyst and 50 kilojoules per mole with a catalyst, both at 298 Kelvin, using the gas constant 8.31 joules per mole per Kelvin. So the first thing we do is write out the equation that we've memorized. So K equals AE to the power of minus the activation energy over RT. And then we just plug in the numbers. So we have A is 6.92 times 10 to the 6. And then we have the exponential. And then we have the power, so minus the activation energy. And because they've given it to us in kilojoules per mole, we have to convert it to joules per mole because the gas constant is given in joules per mole per Kelvin. So we need to times that by 1,000. So it'll be 150 times 10 to the 3. And then we divide that by the gas constant and then times by the temperature, which is 298 Kelvin. So then this comes out to be 3.42 times 10 to the minus 20 seconds to the minus 1. And this is without a catalyst. And then we do the same thing for the one with a catalyst. So we say K is equal to 6.92 times 10 to the 6 exponential to the power of minus 50 times 10 to the power of 3 this time. And then over 8.31 times by 298. And that comes out to be 0.0118 seconds to the minus 1. And that is with a catalyst. And then for B, how many times greater is the rate of reaction with a catalyst compared to without? Well, if we think about it, the rate of reaction is directly proportional to this rate constant. And so if we find out how many times greater the rate constant is with a catalyst compared to without, then that would be equal to how many times greater the rate of reaction is. And so the way we do that is we put the 0.0118 over this 3.40 times 10 to the minus 20. So 0.0118 over 3.42 times 10 to the minus 20, and that gives us 3.45 times 10 to the power of 17. And so the rate constant K is 3.45 times 10 to the power of 17 times greater, and so the rate of reaction is this many times greater as well. So the rate of reaction is 3.45 times 10 to the power of 17 times greater. So as you can see, doing a reaction with a catalyst speeds up the rate of reaction significantly. Before I go on to number 2, feel free to click off the video and try it for yourself first. So this table shows how the rate constant varies with temperature in the reaction of H2 plus I2 goes to form 2HI. Explain how we could determine the activation energy and Arrhenius constant of this equation. So what we do first is we remember that rearranged equation. So initially we had K equals A e to the power of minus the activation energy over RT. But we have a rearranged version, which looks like this. We have ln K equals ln A minus the activation energy over RT. And what we know is the general equation of a straight line graph, which is y equals mx plus c. So if we just match up some of these things to y equals mx plus c, then we should be able to get a straight line graph. And so if we call ln K y, so if we have y as ln K, ln A could be c, and then we would have mx. And so if we make ln K y, and we have c as ln A, and then we have m as minus activation energy over r, and then we have x as 1 over t, then if we plot a graph of ln K over 1 over t, we'll be able to find the activation energy and the Arrhenius constant. And so what we do is we plot a graph of 1 over t on the x-axis and ln K on the y-axis, and then we'll get a graph that looks like this. And then what we do is the gradient of this graph, which is this m here, will be equal to minus EA over R. So to find the activation energy, what we would need to do would be to find the gradient of the line first of all, and then multiply it by minus the gas constant. And then for the Arrhenius constant, we have this C here, and the C represents the y-intercept. So it's this point here where the line crosses the y-axis. And so this gives us our ln A value. So if we unlog this value, then we should be able to get the Arrhenius constant. And the way we do that is, for example, if we had ln A is 6, just as an example, we would put e to the power of 6 in order to get rid of this natural log. So we would do A equals e to the power of 6, and that's how we would find our Arrhenius constant.